Hello and welcome to a video on the normal distribution. In this video we're going to recognize the characteristics of normal distribution, understand the 68, 95, 99, 7 rule, or sometimes called the empirical rule, find scores at a specified number of standard deviations from the mean, use that empirical rule, convert items to a z-score, understands percents and quartiles, interpret margins of error, and recognize when distributions that are not normal. Alright, so a big section, a lot of stuff going on here. Alright, normal distribution. So we've kind of talked about it already. That's our bell-shaped distribution. So we've seen these bell curves before. I think we've just called them bell curves. I don't think that I slipped out the word normal distribution. I may have, because they are the same. When we see that bell shape, a lot of times you'll hear me say normal or in the normal distribution. But what we have is a single mode, and we're symmetric about the mean, and symmetric about that, well, that mode, which is the mean. The mean, median, mode are all equal when we're talking about a normal distribution. All right, the shape of the normal distribution. It's like a combination of the mean and the standard deviation. So what we have right here is a mean with 3 different standard deviations. The first one over here on the left, it's a very narrow standard deviation. The standard deviation, remember, is the measure of the spread in the data, but technically it's the measure of spread around the mean, like as we move away from the mean. So small standard deviation, a really skinny bell curve, then a middle range standard deviation, then a bigger standard deviation. We get a lot of spread in our data and a wider bell. Alright, the 68, 95, 99, 7 rule, or sometimes called the empirical rule. So what this says is, it's basically the amount of data that falls within a certain amount of standard deviations. So it says approximately 68% of the data falls within 1 standard deviation of the mean, right? And then around 95% of the data falls within 2 standard deviations of the mean, and that means down 2 deviations and up 2 deviations. And then around 99.7% of your data is going to fall within 3 standard deviations of the mean. So 3 down and 3 up. So the negatives here are just how many deviations down and how many deviations up from the mean. Alright, finding scores from a specified deviation from the mean. So we have adult heights in North America, approximately normal, mean of 70 inches, standard deviation of 4 inches. Find the height that is 2 standard deviations above the mean. So like, what's the cutoff at 2 standard deviations above the mean? So what we do is we take the mean and we're going to multiply 2 standard deviations and add that to the mean. So 70 plus 2 times 4 is 78. So that's 78 inches, and this is also inches, is the height that would be 2 standard deviations above the mean. So it does have the same units as the original data set, the mean, and the standard deviation. Notice it also has the same units as the mean. Alright, let's try to use this 68, 95, 99, 7 rule. So looking at this picture, the same heights, the males that were distributed, that we're talking here, the mean is 70, standard deviation of 4. So this is how that would be distributed using that same picture that we used. So this is what we used before, with 0 being the mean, 1 standard deviation up, 2 up, 3 up, 1 standard deviation down, 2, 3 down. Well, if the mean was, like it was on the last one, 70, and the standard deviation is 4 inches, then that would become this: 70, 74, 78, 68, 82, and 76, 66, 62, 58 on the way down. So this says use the distribution to the right to find the percentage of men in North America with heights between 66 and 74 inches. Well, notice right here is 66 and there's 74. That's 1 standard deviation down and 1 standard deviation up. So that ends up being 68, about 68% falls in between those two. Alright, that's the empirical rule, the 68, 95, 99.7 rule. That's 1 down, that's 1 up. So that is the empirical rule. Okay. So one deviation down, one deviation up, so it's about 68%. But you can just use it from here. What you may want to do is take this image right here and just draw that picture, and just put 0, 1, 2, 3, negative 1, negative 2, negative 3, and then when it becomes time to actually do one of these problems, right below the 0, write what the mean would be. The mean was 70, so we put that right below the 0, where the 0 was, and then add 4, add 4, add 4, subtract 4, subtract 4, subtract 4. And then you have your numbers, and you can just look and see. And between these two numbers is 68%. Z-scores. So what a Z-score is, it's just a count of how many standard deviations something is above or below the mean. Okay, the above or below part will come from the sign. If it's a positive Z-score, then you are above the mean, because this is where the sign is going to come from, the numerator. So positive means the data item was bigger than the mean. When we subtracted, we got a positive number. But if we get a negative, that means we're below the mean, and that means this data item minus the mean would have been a negative number because the mean was bigger. Standard deviation is always positive, so we end up with z-scores of positive being above and z-scores of negative being below. Alright, if you happen to have a z-score that is the mean, that they're exactly equal, the data item minus the mean, since these two things will be the same, will give you a 0. So the z-score for the mean is 0. So that's kind of like what this was up here. So that's the mean, and then this one standard deviation up, one standard deviation back. These are like z-scores on this picture that we saw before. So the z-scores kind of guide the 68, 95, 99, 7 rule. It's just we plug in the numbers there when it comes time to actually do the problems. Alright, let's look at computing a z-score. So we got a mean weight, so the mean is 7 pounds, standard deviation is 0.8 of a pound, and we've got a newborn infant, so normally distributed. Find the z-score for a weight of 9 pounds. Now, for stuff we're going to do later, this is important, that the weights of the newborn infants are normally distributed, but for z-score purposes, we don't really need to know that. For z-scores, a z-score is a z-score. So we take the weight that we're given, 9, we subtract the mean, and we divide by the standard deviation. So what would that look like? Data item minus the mean divided by standard deviation. So 9 minus 7 divided by 0.8, 2 divided by 0.8 gives us about 2.5 for our standard deviation, or sorry, for our z-score. Okay, and just notice this notation. Z9 in this particular distribution, that would be the notation for the z-score. 9 is the item that we were using. Alright, so whatever is written right here is what we replace right here in the computation in the formula. Okay, so the Z9 means if we took 9, subtracted the mean, divided by the standard deviation. So this is the z-score for the measurement from the data set, being 9. Alright, IQ scores are typically normally distributed. So what would it mean if we had an IQ score, a z-score of -1.5 if we're dealing with IQ scores? Well, that means that we are 1.5 standard deviations below the mean. So we're going to take 1.5 and multiply that by the standard deviation and subtract that, because it's negative, from 100. So 100 minus 1.5 of these standard deviations, 76. So the z-score of -1.5 would correspond to an IQ score of 76 in that particular distribution. Alright, percentiles and quartiles. Percentiles are the percent cut points that are below some particular value in a data set. So for instance, the median that we've studied in previous sections, the median is the 50th percentile, because 50% of the data is less than that number, less than the median. Alright, but we could pick any percent to be percentiles. We could pick the 20th percent, the 9th percent, the 100th percent, which we typically wouldn't, but the percent is just what number is the cutoff to where that percentage is less than that number. Alright, and then quartiles are using numbers that are significantly and meaningful, numbers that we are more likely to be interested in, like the 25th percentile and the 75th percentile. Okay, the 50th percentile, the median, is also called a quartile, but again, we call that the median. That's typically what we refer to that as. But the 25th percentile, the first quartile, or the 75th percentile, which is the third quartile, are special percentiles that we calculate a lot, especially when we're talking about distribution of data. Alright, so let's think about z-scores and a table of z-scores. You can find the percentage of data items that are less than any number if we have a normal distribution. So now, with this z-table that we're talking about, it's now required, we have to have a normal distribution to be using this table. Okay, so just know that what I was talking about up here, if you're just computing a z-score, it doesn't matter what the distribution is. It always told us that it was normal, but that didn't really matter as far as z-scores go. But now that we are using the table, which is called the z-table, now we have to have a normal distribution to do this. Alright, so in a normal distribution, the mean, the median, mode all have that z-score of 0 in their 50th percentile. 50% of the data items are bigger than the mean, and 50% of the data items are smaller than the mean. Alright, margins of error. This is a very normal thing that's done, especially in an election year. So in election years, you always hear of, this is the candidate we predict that will win the race, and this is the percent in a poll that said they would vote for this candidate. And if it's a good statistical service that's giving you this data, they will give you the margin of error in that poll as well. And that comes from the fact that they're using a sample to estimate what's going to happen with the population. And because there's this uncertainty level, that's where the margin of error comes in. So we can use properties of the normal distribution to estimate the probability that what we get from a poll reflects what is actually happening, what we are going to see. So if n is a sample size, it's how many people are in our sample, in our poll, then there is a 95% probability that the true value of whatever the poll is, the percentage of the poll, lies within 1 divided by the square root of n, the square root of the sample size, of the true population parameter, or the statistic for the population. So what that means is if we get a sample, and that sample of 100 people says that 52% are going to vote for some candidate for mayor, then if we take that percentage and multiply this 1 divided by the square root of the sample size times 100%, add and subtract that to our poll, then that's what we get the margin of error. It's what we're saying is that there's a 95% chance that it really is in this number here. So let me just show you what I mean here. So I had 52% was my my estimation from the sample. So let's say again that I had 100 people in my sample. So 1 divided by the square root of 100. Alright, that's 0.1. So if I multiply that by 100%, so times 100%, alright, so that's 10. I said it was 52% people in the poll. If I subtract that 10 and then I add that 10, what I'm saying is somewhere between 42% and 62% is the true value of the population of the voting population that's going to vote for that candidate. Alright, now if I increased that sample size to, like, say 1,000, or let's do 1,500. If I made it a big sample, I get that, and then times 100. Now I'll just have to go down 52 minus, I'm going to say 2.58, and 52 plus 2.58. When we get a big sample, we can really tighten that window of where we're 95% certain that true population percentage falls. So that's what this number is representing, is how tight the window is going to be from our estimate, from the sample. This is what our sample estimate was, and this is using this value, this property of the bell curve, we can kind of squeeze it into this tiny little window of what the actual population percent is going to be. Alright, so let's do another example using the same concept. So in a random sample of this many, 1,172 children, 17% of those said that getting bossed around is a bad thing about being a kid. So we're going to start off with that 1172, that's our n. We're going to take 1 divided by the square root of that. That's 2.9%, and we're going to add and subtract that from the 17%, and that's like the lower bound and the upper bound. So we're 95% certain, there's a 95% probability that the true population percentage for all kids that feel this way is between these two numbers, 14 to almost 20%. Alright, that's called the margin of error. Now that's a bell curve. Not everything is a bell curve. We have other kinds of distribution. Alright, this is what we call a right skewed distribution. So a right skewed distribution has a tail that's longer to the right. It's not symmetric at the mode anymore. And when that happens, remember we have skewness to the right. That means that there are these bigger values, these extreme values to the right of the mode and the median are much bigger than the extreme values that are to the left. Like what I'm saying there is that this distance right here is way less than this distance. And because of that, remember that the mean is more influenced by extreme values than the median is. So notice the mean gets pulled up off of the mode more than the median does. Right? The median only gets pulled up to here. The mean gets pulled off the mode all the way up to here because of the fact that the right tail from the mode is much longer than the left tail is. Okay, so when we have skewed data, when data is skewed to the left or the right, the mean always gets pulled in the direction of the skewness. So on the number line, if the data is skewed to the right, the mean is going to be higher, meaning because it's pulled to the right. Alright, now flip the image just to make the left tail now longer, and notice the words are all backwards, but there's the mode, there's the median, and now the mean gets pulled down further to the left. And again, if this is the number line, remember numbers are getting bigger left to right, so that means now the mean would end up being smaller than the median. It would get pulled down. So when that happens, just know the mean always gets pulled in the direction of the tail of the distribution.